Have you ever stopped and just wondered how your computer does it all? You're streaming music, you've got a dozen browser tabs open, notifications are popping up, and the whole thing doesn't just crash and burn. It feels like magic, right? But what's really going on is this incredibly complex technological ballet, all happening behind the scenes to keep things running. So let's pull back that curtain and see how it really works.
Well, the secrets, it lies with the master conductor of the whole show, the operating system. It's constantly making these split-second decisions about what gets to run and when and for how long. But how does it decide? And what happens when all those different programs actually need to talk to each other? That's exactly what we're going to break down.
All right, here's our game plan. We'll start with how the OS juggles all these tasks and solves the big priority problem, deciding who gets to go first. Then we'll dive into the challenge of sharing information, which, believe me, can lead to some seriously chaotic situations. And finally, we'll see how the system brings order to that chaos with a really powerful concept called the critical section.
So first up, solving that priority problem. Just imagine dozens of programs all lined up, all demanding the processor's attention at once. The OS can't just pick one at random. It needs a system. It needs a way to create like a VIP line for the most important tasks. And one of the first clever solutions is something called multi-level queue scheduling. The key idea here is just to get organized. Instead of one giant, messy line of programs, the operating system sorts every single task into separate queues. Think of them like different waiting rooms, each with its own level of importance. Yeah, this image is the perfect way to picture it. It's kind of like a nightclub with different entry lines. The scheduler, it acts as the bouncer, and it will always serve the highest priority line first, no exceptions. Only when that top-tier VIP queue is completely empty will it even look at the next one down. So, what kind of tasks get that VIP status? Well, think about anything you're directly interacting with, your mouse cursor, the video call you're on right now. Those are what we call foreground processes, and they get high priority. Meanwhile, a background task, like a system update downloading or a file backup running, that gets put in a much lower priority queue. Makes sense, right? But there's a pretty big catch with this simple system. See, once a process gets assigned to a queue, it's stuck there, for good. But what if a background task suddenly becomes super important? Or what if a high-priority task starts being a resource hog and slowing everything down?
And that brings us to the next evolution, the multi-level feedback queue. The crucial difference, as you can see right there, is that it's dynamic. Instead of being stuck in one place, processes can actually move between the different queues based on how they're behaving.
This system is just brilliant in how it keeps things fair. If a high-priority process gets a little greedy and starts using way too much CPU time, guess what? The OS can just demote it to a lower priority line. And on the flip side, if a process has been waiting patiently in a low-priority queue for way too long, it can get promoted. This whole dynamic balancing act prevents any single task from being starved of resources. It's way smarter. Okay, so we figured out how the OS acts like a traffic cop for all these individual programs. But what happens when those programs aren't just driving in their own separate lanes? What happens when they actually need to merge, cooperate, and share the same stretch of road? Well, that introduces a whole new level of complexity. The solution here is something called shared memory. And you can think of it like two people agreeing to use the exact same whiteboard. The operating system, which normally keeps their notes completely separate and private, basically says, okay, for this one specific area, I'll let you both write on it to pass messages back and forth. Now, this seems simple enough, but it kind of opens up Pandora's box. The processes themselves are now responsible for coordinating with each other. So what happens if they don't? What happens if they both try to update the same number on that whiteboard at the exact same instant? This leads us straight into a classic problem in computer science, a situation that perfectly, and I mean perfectly, illustrates the kind of chaos that can erupt when sharing isn't controlled very, very carefully. Let's meet our two main characters. We have the producer, a process that creates some data, and the consumer, a process that uses that data. A perfect real-world example is a web server. It produces a web page for your browser, which is the consumer. Simple as that. An even simpler way to wrap your head around this is to think of a shared bank account. You've got one process that only makes deposits and another process that only makes withdrawals. Now, the single most important rule here, the one rule you can't break, is that the final balance must always be correct and consistent. So let's set up a scenario. We have a shared number, a counter, and its value is currently 5. The producer's job is to add 1, which should make it 6. The consumer's job is to subtract 1, which should make it 4. Pretty straightforward, right? But here is the million-dollar question. If they both access that number at the exact same time, what's the final value? I mean, logically, if you add 1 and then subtract 1, you should end up right back where you started at 5. But that's not what happens. And welcome to what's called a race condition. This is what happens when the final outcome depends on the totally unpredictable timing of who gets there first. For instance, what if the consumer reads the value 5 before the producer has a chance to save its new value of 6? Now, both processes are working with old, outdated information. Depending on that split-second timing, the final value could be 4, 5, or even 6. And that level of unpredictability is an absolute disaster for any system that demands consistency. So how on earth do we fix this chaos? Well, the operating system has to step in and provide a way for these processes to share data safely by establishing some very clear rules for orderly access. The solution revolves around this core concept of a critical section. This is the specific part of the code, and only this part, where a process touches that shared data. And the rule is ironclad, it's simple. Only one process can be inside its critical section at any given moment. It's an exclusive one-at-a-time zone. To enforce this, every process has to follow a strict protocol. It's like knocking on a door before you enter a room. First, it runs an entry section of code to ask for permission. Once it gets the green light, it executes the critical section. And when it's all done, it runs an exit section to clean up and signal that the room is now free for the next process in line. Now, any good solution to this problem has to guarantee 3 non-negotiable things. First, mutual exclusion. That's the obvious one, only one process at a time. Second is progress, which just means if the room is empty, you can't just block someone from entering for no reason. And third, bounded waiting, which is super important. It ensures no process waits forever while others keep cutting in line. It's all about being both safe and fair. And this quote from our source material really just nails it. The entire goal is to maintain that data consistency. And to do that, the operating system absolutely has to provide the tools to turn all that potential chaos into orderly, predictable, and safe cooperation. So, okay, we get it. We understand the rules for safe sharing, and we know what a good solution needs to guarantee. But that leaves us with the next big question. How does an operating system actually build the digital locks and the signals to enforce all these rules? Well, that's where the real engineering magic begins.